All right, let's jump right into a classic problem from Irodov, number 1.138. This is one of those mechanics puzzles with a spiraling disk that, when you first look at it, seems ridiculously complicated. But as you're about to see, one single core physics idea makes the whole thing just fall into place.
So picture this. You've got a cylinder just sitting on a surface with no friction. A small disk is tied to it with a thread. Then you give that disk a flick, an initial push, so it starts moving. As it moves, that thread starts wrapping itself around the cylinder, pulling the disk in tighter and tighter and tighter in this spiral. The big question is, how long does that whole process take before the disk smacks into the cylinder?
Now, I know what a lot of you might be thinking. Okay, I need to find the equation for a spiral path. And listen, if that's your first instinct, you are not alone. But trust me, that is the long way home. That path is really messy. So instead of jumping into complex math, let's just take a step back and think about the physics first. Let's build a strategy.
Okay, rule number one for any tough physics problem. Put the calculator down. Seriously. Before we even think about writing a single equation, we just have to get organized. What do we actually know here, and what exactly are we trying to find? It sounds basic, I know, but it is the most important step.
So when we lay it all out, it's not so bad, right? We have three things we know: the cylinder's radius, r, the starting length of the thread, L0, and that initial velocity, V0. We also have a crucial condition: no friction. And our one target, our goal, is to find the time t. So our mission is to build a bridge from what we know to what we don't, using the principles of physics. In mechanics, when things get weird and paths get all curvy and complicated, our most powerful allies are the conservation laws. But here's the thing, you can't just grab one at random and hope it works. We have to be methodical. We need to go down a checklist and see which ones actually apply here.
Okay, first up on our checklist, linear momentum. This is a big one that often trips people up. I mean, the disk is moving, so it definitely has momentum. But is it conserved? Does it stay the same the whole time? Let's take a closer look.
And the answer is a hard no, absolutely not. And this is probably the biggest trap in this whole problem. Why? Because there's a force acting on the disk. That thread is always pulling on it. That's an external force, and what do external forces do? They change momentum. And remember, momentum is a vector. It has magnitude times direction. Even if the disk's speed stays the same, its direction is constantly changing, which means its momentum is constantly changing. So linear momentum, off the table. Next. Okay, so momentum was a bust. Let's move on to the next major tool in our toolbox: energy. What about the kinetic energy of the disk? You know, the energy of its motion. 1/2 mv². Does that stay constant? And here we hit the jackpot. Yes, kinetic energy is conserved. And the reason why is all about the geometry. Take a look. The tension force is always pulling inward, right along the thread. But the disk's velocity at any given moment is pointing sideways, exactly perpendicular to that thread. That 90-degree angle between the force and the velocity. That's everything. So why does that 90-degree angle matter so much? Well, it all comes down to the work-energy theorem. All it says is that for an object's kinetic energy to change, a force has to do work on it. And work is basically force applied over a distance. But crucially, the force has to be in the same direction as the motion. Since our tension force is always perpendicular to the motion, it's doing zero work. It's pulling for sure, but it's not actually speeding the disk up or slowing it down. And if the work done is zero, the change in kinetic energy has to be zero too. And that, right there, is the big aha moment. That's the key that unlocks this entire problem. If the kinetic energy doesn't change, it means the disk's speed can't change either. So despite that whole complicated spiral path, the disk is just cruising along at its initial speed, V0, the entire time. This simplifies things a lot. Now, just to be thorough, let's quickly check our last big conservation law, angular momentum. Is it conserved in this system, say about the center of the cylinder? Yep, turns out it is. Torque is what changes angular momentum, and you get torque from a force that's applied at some distance. But since our tension force is always pointing right at the center of rotation, it has no lever arm, which means it creates no torque. So angular momentum is conserved. Now, we could totally solve the problem this way, but honestly, the fact that the speed is constant is a much, much simpler path to the answer. So let's stick with that. All right, we have our golden ticket. The speed is constant at V0.
So now we can shift gears from thinking about physics principles to actually doing some math. Let's use this insight to build an equation and solve for the time.
So you might be tempted to just use a simple formula, like distance equals speed times time. But we can't do that, can we? Because the radius of the disk's motion, the length of the unwrapped thread, is constantly shrinking. This is a perfect job for a little bit of calculus. And don't let the term differential equations scare you. It just means we're going to look at what happens in one tiny little instant, and then add up all those instants to get the total picture.
Okay, here's our mathematical game plan. First, we connect the disk's constant linear speed, v0, to how fast the thread is wrapping. That's v0 equals L d theta dt. Next, we need a formula for that changing length L. Well, that's just the starting length, L0, minus the bit that's already wrapped up, which is r times the angle theta. Step 3, we just plug our expression for L from step 2 into our first equation, a little rearrangement, and we get a neat little relationship that connects a tiny bit of time dt to a tiny change in angle d theta. And finally, to get the total time, we just have to sum up all those little bits of time. And how do we sum up an infinite number of tiny things? We integrate. And this is what that setup looks like. We're going to integrate the left side from our start time of 0 up to our final time t. And we'll integrate the right side from our starting angle of 0 all the way to the final angle when the thread is completely wrapped up. Now it's just a matter of solving this pretty straightforward integral to get our answer. And boom, there it is, the time it takes for the disk to hit the cylinder. And it's always a good idea to just do a quick sanity check. Does this answer make sense? Well, time goes up with the square of the initial length, so a longer string means way more time, yep. And time goes down if the radius or the initial speed are bigger, so a faster disk or a fatter cylinder means less time. That checks out. The physics feels right. So we got the answer, which is great. But the answer itself isn't really the most important part of this exercise. What's truly valuable is the process we used to get there. This is a blueprint, a strategy that you can use for all sorts of tough mechanics problems. Think about what we did. We started with what looked like a total mess, but we didn't panic. We just broke it down into what we know and what we want. Then, we analyzed the forces and systematically checked our big conservation laws. That gave us our key insight, the constant speed. And once we had that light bulb moment, the rest was just connecting it to the geometry of the situation. This method turns confusion into a clear, repeatable plan. And really, this is what physics is all about. It's not about memorizing a giant book of formulas for every possible situation. It's about understanding a small set of incredibly powerful core principles so well that you can see which one is the key that just slices right through all the complexity of a problem. And I promise you, this way of thinking goes way beyond mechanics. You will use this exact same strategy, systematically checking for what is and isn't conserved, in electromagnetism, in thermodynamics, even in quantum mechanics. It is one of the most powerful tools you have. This really sums up the difference in approach, doesn't it? A common pitfall is to just start guessing formulas, trying to brute force the geometry, and getting completely stuck. The expert approach is to step back, analyze the physics first, and let the conservation laws show you the simplest, most elegant path to the solution. So, I'll leave you with a final little question to think about. We found the total time it takes for the disk to hit the cylinder. So, how would you calculate the total distance it traveled along that spiral path? With what we discovered today, the answer is actually incredibly simple. Thanks for joining this explainer.